All right, guys, let's go ahead and pick up where we left off from class today. I'm going to start off with question number 10. Now, this is second fundamental theorem of calculus again. We saw one earlier today, and that one was pretty simple, but this is the more complicated one. I gave you a formula like this in slide 19 of your Unit 6 review, but basically it was something to this effect here. I'm going to be changed. It won't be the same letters because I'm just making this up off the top of my head right now. But the formula looks something like this. So here's how it works. You take this, if you want to take the derivative of this thing, okay, that's our goal. This drops down inside. This drops down inside as well. And then we subtract those. And they also get multiplied by the derivative of the inside. Now, I'm not going to go into why this formula came about. You can go back and watch that lesson if you want to. I doubt you'd want to do that at this point. But that's the process there. All right? So we're going to take this. If I want to find the derivative of this expression, we're going to take this 4x squared and drop it down in there like so. We're going to take this 5 and drop it on in there as well like so. The derivative of the inside here is 8x, and the derivative of the inside here is 0, so this whole piece goes away, and this is what I'm left with. Okay, so that's the second fundamental theorem of calculus. Moving on to question 11, they give us an integral function, and they say, what are the least number of critical values of g? Well, critical values are those places where the derivative equals 0. Now, so we have to find the derivative. Well, g prime is equal to the derivative of this. Now, applying the second fundamental theorem of calculus, we find out that it's just simply f of x. Okay, so if I want to find where g prime equals 0, basically that means I need to find where f equals 0. Now, if you're looking at f here, you'll see that there's nowhere where f seems to equal 0, but that doesn't mean f doesn't equal 0. It just means they don't have that one in the table. You could tell when f is equal to 0 by using the intermediate value theorem. If I go from 5 to negative 6, would I have to cross 0 at some point? Yes, I would. And if I'm going from negative 6 to 8, would I have to cross 0? Yes, I would. And if I'm going from 8 to 2, would I have to cross 0? No, I would not have to do that. How about if I'm going from 2 to negative 6? Yep. How about from here to here? Nope. And from here to here? Yep. So there are 1, 2, 3, 4 times for this particular example that I'm sharing with you where you would have to have a critical value. It could be more. Like there could be a place where the function equals 0 in here, but it's just not necessary. But there has to be at least 4 places where there is a critical value of g. All right, let's go ahead and take a look at question 12. The graph of h is given below. If g is equal to the integral of h from 0 to x, where g is both increasing and concave down. Oh, it's asking where is g both increasing and concave down. So g is increasing when g prime is positive. Okay, so what's g prime? Well, g prime would be the derivative of this function here, which is simply h. The derivative cancels out the integral, and you're left with h. So g is increasing when g prime, which is the same thing as h, is positive. In other words, when h is above the x-axis. So g is increasing here and here. That's where g is increasing. Now let's move on to the next part. They also want to know where it's concave down. So g is concave down when g double prime is negative. Well, if g prime is h, then g double prime is h prime. Okay? This is the derivative of this graph. which means it's the slope of that graph. So G double prime is H prime. So to restate the fact, G is concave down when G double prime, which is the same thing as H prime, is negative. So for our graph, in other words, we're looking for where H has a negative slope, or you could say is decreasing. Okay, so I'll highlight this one in blue. We have a decreasing slope here. We also have a decreasing slope here. Now we're looking for the portions of our graph where G is increasing and also where G is concave down. So in other words, we're looking on the graph where both red and blue happen simultaneously, and that's this area right here. So that's for all numbers less than -3. You could write it like that, from negative infinity up to -3 is where G is increasing and concave down. Right? So that's your help for number 12. For question 13, all you have to do to find the integral that they're asking for is just to find the area under the curve, but you do want to remember that anytime area is under the curve, it is negative, or sorry, under the x-axis. Let's take a look at question 14. So in question 14, they give you the value of two integrals, that one and that one, and then they ask you to find this one. So the trick here is in applying the properties. You could take this integral and apply it to the functions separately. So in other words, you could write it like this. And now that we've done that, we could just look at our references that they gave us. They told us that this one is equal to 2. And they tell us that this one is equal to -8. So I've got 4 plus 24, which is 28. Okay? Moving along. Question 15, they want us to integrate a piecewise function. Now, when you integrate a piecewise function, you need to break it up into its pieces. So, I want to find what is the integral from -3 to 5. Well, to do that, I need to split this integral up into some pieces. So I'm going to start at -3, and for all x less than 0, we're going to use this. So from -3 up to 0, it's 2. Plus, the next integral picks up where that one left off at 0, and it will keep going until we get to 4. And for that piece, we're integrating 3. The next piece picks up where the last one left off at 4, and after that it's going to keep going until we get to where we want to stop, which is 5. And we're integrating that piece there, 5. So for the first piece it's 2, for the second piece it's 3, and for the third piece it's 5. These are the intervals, and we're going from -3 to 5. So from here, we're basically just going to integrate. So the integral of 2 is 2x. The integral of 3 is 3x. And so on. And then we're going to go ahead and plug these in and subtract. So plug in 0, you get 0. Plug in -3, you get -6. So we have 0 minus a -6. Plus, plug in 4, you get 12. Plug in 0, you get 0. Plug in 5, you get 25. Plug in 4, you get 20. And then we just need to simplify all this. So this is 6 plus 12, which is 18. That altogether makes 5. So the final answer is 23. All right, let's move on to the FRQ. So we're not going to do all of the FRQ questions. We're just going to do 1, A, B, and C, and then we're going to do question 2, A, and D. All right, let's go ahead and read our given information first. It says the rate at which water leaks from a container is modeled by the twice differentiable function R. where R of t is measured in gallons per hour and t is measured in hours. So values of R are given in the table above for selected values of t. So this is a rate. It's gallons per hour at which water is leaking from a container. And then we have the top, which is in hours. So part A, use the data in the table to find an approximation of R prime of 1/2. Show the computations that lead to your answer. So this is an instantaneous rate of change. And whenever you have a table problem, you can estimate an instantaneous rate of change by doing an average rate of change using the two values that are closest to the number they give you. So what two numbers are closest to 1/2 up here? That would be 1/3 and 2/3. So we're going to use these numbers. So R prime of 1/2 is approximately equal to the average rate of change of R from 2/3 to 1/3. So R of 2/3 according to the table is 5. R of 1/3 is 8. Simplifying the bottom, we have 1/3. So that's negative 3 over 1/3. Multiplying the top and the bottom by 3, which, by the way, you don't really have to do at this point because we're already done at this step. Technically, you don't have to simplify that, but I went ahead and did it. But let's go ahead and see. So now that is my approximation of R prime. They want to show the computations. I did that, but they want me to also give the units of measure. Okay, so what are the units of R? R is gallons per hour. Notice it's being divided by the time values also, though. So what this is this is gallons per hour per hour. Now some of you guys might think, Mr. Bailey, I thought you said like only double derivatives were per hour per hour. Well, technically, even though it's R prime, that is technically kind of like a double derivative, if you will, because this is a rate. And so this is a rate of a rate, which makes it gallons per hour per hour. Okay? So let's go ahead and take a look at part B. Part B tells us to use a left-handed Riemann sum with 3 subintervals indicated in the table to approximate the integral 0 to 1. Once again, they want us to indicate the units of measure. All right, so here we go. We want to do a left Riemann sum. So first of all, let's find our bases. So from here to here is 1/3. From here to here is 1/3. And here to here is 1/3. So they all have the same base. We start on the left and we do base times height, base times height, base times height, and we leave out the last one. Okay? And so now you could do this on your table on an FRQ when you guys are taking your AP exam, that's fine. But you need to make sure that you show this work in the spot where you're supposed to put your answer. Now technically we don't even have to simplify this. This is good enough as an answer, and I'm not a real big fan of fractions, so I think I'm just going to leave it. So that's the answer to our integral. But they do want us to also indicate the units of measure. So when you integrate, you lose a time factor from the denominator. So what do I mean by that? We're integrating R. R is gallons per hour, right? So if I have this, and every time you integrate, you lose a time factor off the bottom. So this goes away, and the answer is gallons. This also makes sense when you think about rate in and rate out problems. This is like a rate out, and this is the amount that has leaked out on the time interval from 0 to 1 hour. So this is how many gallons have leaked out of the bucket or whatever after 1 hour has gone by. But it's only an estimate, right, of the actual integral, because we don't know what the actual integral is. We're just estimating it with a left-handed Riemann sum. All right, let's go ahead and take a look at part C. Part C says this one. Now, it's important to notice the difference between an expression like this and an expression like this. In our table, we have R. So when you have something like this, the only way you're going to be able to do that with a table is with some kind of a Riemann sum, which is what we did. But in this case, we don't have R prime in the table. We have R. So we can actually integrate R prime. What is the integral of R prime? The integral of R prime is just R. And so we have R of 1/3 minus R of 0, which is 8 minus 11, which is -3. And that's it. That's all they wanted me to do. They didn't ask me to determine what the units were or anything like that. But I mean, I could tell you what the units are. We did R prime earlier on question number 1. Do you remember our units? They were gallons per hour per hour. Well, since we're integrating, we lose one of those. And so this is gallons per hour. And so basically what this tells you is it's telling you that, well, this is how fast the water was leaking out of the bucket at t equals 1/3. This is telling you how fast water is leaking out of the bucket at t equals 0. So this tells us that water over the time interval from 1/3 to 0, the average rate of change, if you want to say that, is -3 gallons per hour. Right? All right. Now, this topic down here on part B, on part D, we're not going to do this, but I do want to just say this to you guys at least. We skipped this. I did not go over this year, and that was on purpose because this concept takes many, many, many days to explain, and ultimately on the AP exam, it comprises only a couple of points. So I figured, you know what, we're going to let that one go. So when you guys see this weird-looking little symbol here, just know that, oh, that's the thing Mr. Bailey did not talk about. And so we're going to leave that behind and just skip those. Put a random guess or something. It's in your textbook, so if you have a lot of free time, and you want to read your textbook and figure out how to do it, you can. It's under the section about Riemann sums, but we're not going to be doing it as a class. So I'm going to be skipping that, and we'll go on to FRQ number 2. So they give us a graph here. And we're only going to be doing parts A, and I forget, what was the other one? We're going to only do parts A and D. So the figure above shows the graph of f prime, which is the derivative of f. The areas of the regions between the graph of f prime and the x-axis are labeled in the figure. So they're telling me that the area of this shaded region here, they're telling me that that's 2. They're telling me that this area is 7, but do keep in mind that that area is 7, but since it's below the x-axis, anytime we do any kind of calculation with it, unless we're doing an absolute value of some kind, that is going to be a -7. Okay, so that's something to keep in mind. So there's our areas, and then they give us an initial condition. So basically we have the graph is given, the graph of f prime, and then an initial condition. So let's go ahead and take a look at A. So the integral of f prime would be, so technically you could integrate f prime and you could get f. Now don't write this because I'm going to tell you what's wrong with this in a second. Because we did that in the last problem. But here's where you're going to run into some difficulties. I have no idea what the function f is. So that's a bad approach to take with this problem. Instead, we can interpret this in a different way. I have the graph of f prime, so what this represents is the area under the curve. So if I'm going from 0 to 7, so from here all the way over here, basically it's just this area plus this area plus this area plus this area. So it's 2 minus 7 plus 3 plus 1. So that would be -5 plus 3 is -2 plus 1 is -1, I think. And that does it for part A. So that was nice. Let's go ahead and take a look at part D. Part D asked me to do the integral of f prime of g of x, so from 1 to 2. So I'm going to bring this back up here and I'll show my work on the side here. So we have, I want to find the integral from 1 to 2 of x, f prime of g of x. dx. All right, well, this is going to be a u sub problem. My u is g of x, and they tell me what g of x is right here. It's 5 minus x squared. So now we find the derivative of u with respect to x, in other words, g prime, which is negative 2x. And then we get the dx by itself. We don't really need to have that there. So if you were to take this expression here and get the dx by itself, you would have du over negative 2x equals dx. And now we're ready to do our u substitution. So I have x f prime, right, of u du over negative 2x. So now these x's go away, and I can also take this negative 2 and bring it out to the front, but it's going to be in the denominator, right? Now another thing that we need to change is the limits. Anytime you guys do a u sub with a definite integral, you need to change your limits. So how do you do that? You take your limits and you plug them into the u function, which is g. So if I were to plug in 2, I get 5 minus 4, which is 1. So the top number becomes 1. We'll also plug in 1. So I'm going to plug 1 into the g function here. 5 minus 1 is 4, so now this is 4. So now as a more cleaned up version of this integral, we have this. And now we're ready to finish the problem. So the integral of f prime is f. Actually, I take that back. Let me back up. Once again, I don't want to make the same mistake I made on part A. We could integrate this and just get f, but we found that didn't go anywhere because I don't know what the function f is. So, but we can do this simply by doing area under the curve, so from 1 to 4. So that would be this area and this area combined. So that would be the following, 2 minus 7. And we could just leave our answer like that. There's no reason to get fancy. That's good enough for an FRQ. Okay? So, there you guys have it. Hopefully it was helpful. We'll see you guys in class tomorrow.